It's Paul Bamberg on a snowy Monday morning with the first of 3 recordings for today's Math 110 lecture. This is going to be the longest of the 3 recordings. I'm going to try to convince you that the power series method for solving second-order linear differential equations converges. So let's look at our typical equation. Our linear operator L of y is some function a of x times y double prime plus b of x times y prime plus c of x times y. We set that equal to 0, and we're assuming that a of 0 is different from 0. Since a is a continuous function, if it is different from 0 at 0, it's different from 0 for some interval around 0, and therefore we can safely divide by it. So to deal with only 2 rather than 3 series, I'm going to divide through by a of x, isolate y double prime on the left-hand side, and set p of x is minus a of x, b of x over a of x, and q of x is minus c of x over a of x. There will be some interval from minus capital R to R on which a of x is different from 0. So here's the equation that we need to solve. Now the general strategy is that we are going to replace these functions little p and little q by functions capital P and capital Q that are bigger. We are then going to set up an equation involving a function capital Y, which is bigger than little y. We're going to show that the equation for capital Y first can be solved, second has a power series expansion which is term for term bigger than the one for little y, and therefore our series little y will converge by the comparison test. There's a fair amount of messy computation where all that ultimately matters is that the calculation can be done. The exact answer doesn't matter, but we still have to work it out. Okay, so we're going to replace our original series by something that's bigger to get a comparison equation, and we'll pick some capital S, any positive capital S that is smaller than capital R will work. And now what I'm going to do is choose a pair of constants. I'll call them capital M and capital N, so that the series for little p of x in the equation we're actually trying to solve is smaller term by term than the series capital X. You will recognize this as the geometric series for the function m times 1 minus s over x, which, as you know, is m times 1 plus the ratio x over s plus the square of the ratio plus dot dot dot. And comparing these, you immediately see that the nth term in the series for capital P is our chosen constant m divided by capital S raised to the nth power. Similarly, for q of x, we are going to use some constant capital N times 1 minus x over s squared, and look at the coefficients of that. Now here we have to be a little bit trickier to sum the series. How do you get a 1 minus x over s squared in the denominator? Answer, you differentiate 1 minus x over s with respect to s. In doing that, you introduce a minus 1 over s from the chain rule, so we better multiply by s to compensate for that. So our function capital Q over x, when expanded, is ns times the derivative of the geometric series 1 plus x over s plus so on, or multiplying through, we have ns times, when we take the derivative, 0 plus 1 over capital S plus 2x over capital S squared plus dot dot dot. There goes Big Ben in the background. So what have we got when we multiply through by s? We find that q sub n is capital N times little n plus 1, where little n is the power of x, divided by capital S to the n. Now, we're given that the series for P converges, and therefore the series little p sub n times capital S to the n converges. If a series converges, its terms approach a limit of 0. The converse, of course, is not necessarily true. And any series that's convergent is bounded, so we can say the absolute value of little p sub n times capital S sub n is going to be bounded. It's going to be less than some quantity capital M, and I will just choose capital M to be greater than the supremum, the least upper bound, of little p sub n times capital S sub n. So now we've got our capital M. Getting capital N is only a little bit messier. We look at the series for little q, and we say little qn times capital Sn is a convergent series, and therefore applying the same line of reasoning, saying that if a series converges, its terms go to 0, and therefore the absolute value of the terms is bounded, we choose our capital N to be the supremum of the absolute value of little q sub n times capital S sub n, but because we had this n plus 1 up here, we have to divide by that. All that really matters is the following. If the absolute value of x is any real number less than s, then the absolute value of little p sub n times x sub n is less than capital P sub n times x to the n, and a similar result holds for the q's. Now we go on to step 2 of the proof, and this is one for which you are going to be held responsible. It's actually fairly straightforward. I think you'll be happy if it shows up on the quiz. What's our comparison equation? The comparison equation is capital Y double prime is equal to m over 1 minus x over s times y prime plus a similar term involving y, where m and n have been chosen in accordance with the results on the previous page. And we can solve this exactly. Remarkably, if we plug in a solution of the form a times 1 minus x over s to the minus lambda power, we'll be able to find a positive value of lambda that does the job. It'll depend on m, n, and s, of course. To start out, I want to be sure that for x equals 0, this comparison function, capital Y, is greater than the solution to our equation that we're going to crank out by the power series method, and we also want to make its derivative 0. So here's our trial solution. Differentiate it to get y prime. We get a minus 1 over s from the chain rule, and so y prime is lambda a over s times 1 minus x over s, but now to the minus lambda minus 1 power. And when we differentiate once more, we get a formula for y double prime that involves 1 minus x over s to the minus lambda minus 2 power. And now you can see when we combine these terms, we're going to be able to factor out a 1 minus x over s to the minus lambda minus 2. So Starting with y double prime, we copy that onto the left-hand side. Now on the right-hand side, we have our term that involves m. We calculated m on the other page. We have m over 1 minus x over s times y prime. That means we multiply by m, and we have 1 minus x over s to the minus lambda minus 2. And working on the term for y, let's go back up where we can peek at it. We have to multiply by n over 1 minus x over s squared. That conveniently makes the exponent minus lambda minus 2, and we've multiplied by n. That all factors out, and we've just got a quadratic equation. The a drops out, and if we multiply through by s squared, we get from the left side lambda times lambda plus 1. On the right-hand side, we have m times s times lambda plus capital N times s squared. Okay, write this in the standard form. Lambda squared plus 1 from here minus ms from here times lambda minus ns squared equals 0. And we can write down the solution by the quadratic formula. Lambda is 1 minus ms plus or minus the square root of b squared minus 4ac, which is 1 minus ms quantity squared plus 4ns squared. Now look at this equation. The constant term in a quadratic is the product of the roots. Since the product of the roots is negative, one has to be negative and the other root has to be positive. So we know that there will be a positive value of lambda that solves this equation. Now let's go ahead and make a big enough. We certainly need a, which is going to be the value of capital Y at 0, larger than the absolute value of y of 0. We also want to make sure that y prime, the coefficient of the x term in our comparison series, is going to be greater than lambda, well, we know that that's greater than lambda a over s, and therefore we make lambda a over s greater than the absolute value of y prime of 0. That's a second condition on a. Both these conditions on a will be satisfied if we choose a to be the larger of the two quantities, absolute value of little y at 0 and absolute value of y prime at 0 multiplied by s over lambda. Once we've made that choice, we can say that the constant term in the series for little y, which is the initial value of y at x equals 0, is going to be less than capital Y. And furthermore, the coefficient y1 in the power series for little y is going to be less than y prime of 0, which is the coefficient in the power series for capital Y. Now what we have to do is show that all the remaining little y's are less in absolute value than the corresponding capital Y's. To do this, we carry out our standard power series construction, but without any dots. We're going to do it very, very systematically. And this is not done out in full in the Holland textbook. It's relegated to a bunch of exercises. And furthermore, there's a small error in the final formula. This is, however, a very useful skill for almost any sort of physics or applied mathematics. So watch carefully. First, we start with our power series expansion for y, summing over j from 0 to infinity. We differentiate that term by term and get the derivative of y sub j x to the j, which is, of course, j y to the j x to the j minus 1. And we note very carefully that this sum only runs from j equals 1 to infinity, because the term for j equals 0 has a 0 in it. Differentiating yet again, we get j times j minus 1 times y sub j times x to the j minus 2. And again, the powers of x start at the 0th power. That is, j runs from 2 to infinity. What we want to do is to generalize our power series technique. That is, we're going to say for each x sub n, the coefficient has to be equal on the left-hand side and the right-hand side, and setting those two coefficients equal will give us a formula which will calculate one new value for little y. Let's start out by looking at y double prime. X is raised to the j minus 2 power. We want the coefficient of x to the n, so we set x equal to j minus 2, whereupon j becomes equal to n plus 2. And here's a rewrite of our formula for y double prime. It's now a sum over n. N goes from 0 to infinity. J gets replaced by n plus 2. J minus 1 gets replaced by n plus 1. Y sub j by y to the n plus 2. And x to the j minus 2 by x to the n. There's only one term here, but that's not going to be the case with the two terms on the right-hand side, because the next term we need is p of x times y prime. P of x is a power series, and y prime is a power series. And looking at the exponents, we see x to the I and x to the j minus 1. When we multiply those two series together, we're going to get for our value of n, the exponent for x, n equals I plus j minus 1. And therefore, solving for I is equal to n plus 1 minus j. Since the lower limit on I is I equals 0, we know that that quantity is always going to be greater than or equal to 0. So now let's do our rewrite. We're going to be summing over n from 0 to infinity something times x to the n. The something we're going to be summing is itself a sum over j, but looking at the fact that n plus 1 minus j is always greater than or equal to 0, we can see that our sum, which starts at j equals 1, is going to have an upper limit of n plus 1. And what are we going to get? We're going to get j times y sub j multiplied by p sub I, but I is n plus 1 minus j. So this is a rewrite of that product of sums expressed as an inner sum and an outer sum over n. Let's play the same game with q of x times y. It's a product of the series for q times the product of the series for y. We have an x to the I times x to the j when we multiply it out, so we set n equals I plus j. Solve for I, it's n minus j, and note that that is greater than or equal to 0. So when we rewrite this, we'll have a sum over n from 0 to infinity, and for each individual n, the lower limit on j will be 0, and the upper limit will be n, because n minus j is I, and I can never be less than 0. So let's just compare the coefficients of x to the n on both sides. For our y double prime, there's the coefficient. For p times y prime, here is our coefficient, and for q times y, here is our coefficient. And what do you know? We have an explicit formula for y sub n plus 2 in terms of little y for values of j that run up to n plus 1 in the first sum and only up to n in the second sum. So this is the complete version of what we have worked out in special cases in the past. Knowing all the y's up through y sub n plus 1, we will be able to calculate y n plus 2 and crank out the series one term at a time. I've taken the trouble to write out the specific special cases for n equals 0, 1, and 2. You can check those for yourself if you like. And now, remarkably, we're almost done. We started with little p. It's analytic, can be expanded in a power series. And we had our comparison coefficient function, which is m over 2 over 1 minus x over s. I can write those coefficients as p0, p1, p2, and so on. And we made m large enough that for each subscript, the absolute value of little p sub n is less than capital P sub n. Similarly, we arrange things that the absolute value of little q sub I is less than capital Q sub I for all values of I. Now, lambda is positive. This function has a binomial expansion. All the coefficients are positive. We've called those coefficients capital Y sub I. And furthermore, this series converges on the interval from minus s to s, where x over s is less than 1 in magnitude. Now let's look at the formula we derived and finish the proof. Here's our formula for little y n plus 2. It involves sums over little p, little q, and little y, and all the signs in these summations are plus signs. There are no minus signs. All we have to do is show that the series for y sub x is term by term less than the series for capital Y, and we can invoke the comparison test to say little y is also a convergent series. The series for capital Y, as I've said, converges by the binomial expansion. Now, to get things started, let's go back to the way we chose A. We chose A so that the absolute value of little y naught is less than capital Y naught, and the absolute value of little y1 is less than capital Y1. So for the 0 term and the 1 term, little y is less in absolute value than capital Y. Now let's look at capital Y2. If you understand this case, you understand the whole argument. We have an explicit formula for capital Y2 in terms of capital Y for 0 and 1, and capital P0 and capital Q0. We have the same formula for little y2 in terms of little y1 and 0, P0, and Q0. This is less than absolute value than that. This less than absolute value than that. This less than that. This less than that. And it follows that capital Y2 is less in absolute value than the positive quantity capital YQ. There are messier and messier formulas for n larger and larger, but they all have the same property that there's nothing but plus signs in them, so it follows that for all little n greater than or equal to 2, the absolute value of little yn is less than capital Yn. Or, when we multiply through, the term in the series y sub n x to the n, even with an absolute value sign on it, is less than capital Y sub n times x to the n. But the sum of capital Y sub n times x to the n is a convergent series. It converges because it's a binomial expansion. Since little y sub n is less than in absolute value than capital Y sub n, the series with the little y's in it must converge, and furthermore, because of the absolute value, it converges absolutely on the same interval, and we are done. We have shown that there is some interval from minus capital S to S on which the series we crank out by our power series expansion method has the property of converging. The power series solution has a positive radius of convergence.